Let's look at today reactions of ketones. In this case, it's similar to aldehydes, but aldehydes are much more reactive. So here again, oxygen gets the delta negative and the electrophilic carbon gets the delta positive. This nature is there, but it's going to be minimized because of the R groups are electron donating groups, methyl, ethyl, propyl, and so on. So therefore, this is less reactive compared to aldehydes, because aldehydes have a hydrogen, it doesn't really donate electrons. That's the big difference in reactivity. So we're going to do the same reaction. So electrophile and a nucleophile reagent, something like HCl, can be attracted to the delta O negative, the electrophilic portion, and the nucleophilic portion should go to the electrophilic carbon on the carbonyl, right? So we can get an example like hydrochloric acid or HCN. So, and also if you pay attention to for the multiple choice questions, so here we have sp2 120 degree bond angle and trigonal planar species, and then after the reaction, so let's say this HCl is added, right? And what happens now? So we're going to keep the single bonds of R to the carbon, carbon to the oxygen, and the pi bond is the one actually broken, right? So O negative will be neutralized with the H plus if it is HCl, and then the Cl, the nucleophile, will be attached. So now the hybridization turned to sp3, bond angle is 109, it's a tetrahedral. So that kind of the things that you want to expect for questions, right? So sp2 120 trigonal planar changes into sp3 109 tetrahedral. And also the big difference is less reactive compared to an aldehyde, right? And reason, electron donating groups attached to each side of the carbonyl. So let's compare the similar way like we did for the last one. So we take few ketones. So we have just the symbol RC double bond OR, and then acetone, or you can say propanone or acetone, and then yes, let's look at how to make the ketone. So secondary alcohol, PCC, or any oxidation actually will give you a ketone. Remember, secondary alcohol, that's an important thing, right? Now, typically for aldehydes, we did the oxidation. Let's see what we can do with oxidation. So oxidation means bunch of oxygens, let's say permanganate, dichromate, chromate, something like that. And under acidic conditions, we react to see if we can do the oxidation, right? Now, remember aldehyde did oxidize up to carboxylic acid. Here, nothing. The reason is there's no hydrogen on this carbon. So ketones will not oxidize. So only thing you, that's it, no oxidation, right? So let's look at the other side, the reduction, the adding hydrogens in this case, right? So we can actually use lithium aluminum hydride, and well, there is a workup and it's just the reagent there, but I'm just gonna put the lithium aluminum hydride, and we will end up with the secondary alcohol. So basically it's going back where we started actually, right? So that's the reduction, no oxidation, the reduction takes place, right? So now the other reactions, actually the common ones we saw in the aldehyde reactions, it's going to be almost the same thing. This one is actually imine production or imine synthesis, so under acidic conditions. And what happens is this two hydrogens and oxygen we can kind of boxed out, and simply we can put the double bond O replaced by the double bond N, right? And that's an imine. So I'm just going to copy this here, the ketone, and so we will have, yes, so the nitrogen double bond and the whatever the alkyl group we have, maybe methyl, something like that, and it is an imine. So imine synthesis, imine formation can be done under acidic conditions, right, with an amine. That amine will become an imine because of the double bond O, right? Okay, so we figured out no oxidation, but the reduction happens. Now we have another specific reduction with zinc, mercury, and conc HCl treatment. So this will basically remove this oxygen completely. The oxygen is gone. So when the oxygen is gone, it's a reduction. We expect two hydrogens to go there, and that's what happens. So now you have an alkane basically, right? Because you have all the R groups as it is intact, and the oxygen is gone, and then the two hydrogens in that place, right? So that's a specific reaction. And few other reactions, the common ones we saw in the aldehydes. So let's look at that one. So mostly the MCQ questions for the high school exam and the IB, right? The 2,4-DNP treatment, I think I remind you that one. So this is a qualitative test we can do. So in the, yes, 2,4-dinitrophenylhydrazine, this is the reagent. We're going to treat with this one. And so if we do have ketones, and we can kind of simplify this reaction with the similarly to the imine formation, these H2 can take out, let's say we are using acetone as a ketone and this oxygen on the ketone. So these two oxygen and the hydrogen goes away. So then the double bond O is replaced by the nitrogen, actually the first nitrogen, right? So then still the hydrazone is there, and this one will make a yellow precipitate. So that's the qualitative test. So we can recognize by the color the presence of ketones. Now another important thing, if you remember, tolerance and failings will not react with the ketones. Okay, but the Grignard will. So the Grignard reagent, R is a nucleophile, and it can attack to the electrophilic carbonyl, right? Because we get R minus basically from Grignard, right? So that will react. And in this case, just to recognize, I put an R3, and then if we take acetone again, and it will attack to the carbonyl carbon, and then the O negative will become an OH, and this will be a tertiary alcohol. Now, so we actually can make from ketones secondary alcohol and tertiary alcohol and alkanes. So quite a bit of things. Now HCN addition is formation of the, well, there is sodium cyanide or KCN with HCN presence to enhance the reaction. So the cyanohydrin, you can do the reaction. Give it a try.